Good morning. Here we need to find the range, rank, null space and nullity of transformation T that is defined by TAB equal to A plus B A minus BB. And T is a linear transformation from V to R into V3R. So before starting with the solution, we need to first go through the concept. What is range, what is rank, null space and nullity? So let's recall all the definitions for this first. Range of linear transformation. If T is a linear transformation from UF to VF, these two are the vector spaces. U and V are the vector spaces over the field F, right? And T is a linear transformation from U into V. Then the range of T is a set of all the vectors beta in V such that this beta is equal to T alpha for alpha present in U vector space. So RT becomes all those T alpha belonging to V such that alpha belongs to U. Next is the null space of linear transformation. Again, if T is a linear transformation from U into V, then the null space of T is a set of all the vectors alpha in U such that when we apply T on this, that is T alpha, that will be equal to 0. This 0 is a 0 vector of V. And null space is denoted by NT, so NT will be equal to all those alpha belonging to U such that T of alpha equal to 0, where this 0 is a 0 vector of V. If we regard this linear transformation as vector space homomorphism, from U into V, then this null space of T is also called the kernel of T. So you can denote this null space to be as NT or the kernel T, KERT, right? Next is the remarks for the UGC Net Maths exam. If UF and VF with the two vector spaces and T is a linear transformation from U into V, then first remark, the kernel of T or the null space of T is a subspace of U, the vector space U, right? This null space or kernel T will be the subspace of this vector space U. Second, the range of T is a subspace of V. Please remember, but the range of T will be the subspace of V. Next, if U is finite dimensional, the range of T is a finite dimensional subspace of V. If this U is finite, if it is of finite dimensional, then this range of T is also the finite dimensional subspace of this vector space V. Next is the rank and nullity of linear transformation. If T is a linear transformation from UF into V, where this U is finite dimensional, then the rank of T, that is denoted as rho T. This is a dimension of range of T. First we get the range of T and then we find the dimension for this. The range of T is a subspace of VF. It is a finite dimensional because U is finite dimensional. So what is rho T? That is, what is rank T? It is a dimension of range of T. Then the nullity of T is denoted by NT, or just make a stylish N like this. This is the dimension of the null space of T. Now null space of T is a subspace of U vector space, right? So nullity is a dimension of the null space of T. So NT is equal to the dimension of capital NT or the kernel T, right? Small n is for the nullity and capital N is for the null space. So when we find the dimension of null space of T, we get the nullity. Then is very important rank nullity theorem. Let U and V be the vector space over the field F and T be the linear transformation from U into V, and suppose that U is finite dimensional, then rank of T plus nullity of T is equal to the dimension of U. This is a rank nullity theorem. We can find any one of these from this result if other two are given. Now let's move on to our example. We need to show that this T is a linear transformation which is defined by this, and also we need to find the range, rank, null space and nullity, right? So first we need to show that this T is a linear transformation. To show the linear transformation, we need to take two elements from this vector space, let's say alpha and beta, and two elements from the field, let's say A and B, right? We need to show that T A alpha plus B beta should be equal to A T alpha plus B T beta. We need to show this for the linear transformation, where alpha beta belongs to the vector space V2 and A and B are the elements taken from the field R. So let alpha be equal to A1 B1, because we are having V2, the two-dimensional vector space, so we have to take A1 B1. That is why we have taken alpha to be A1 B1. Take beta to be equal to A2 B2, which are belonging to the vector space V, the two-dimensional vector space. Then what is T alpha? T alpha will be equal to T A1 B1, right? And this T is defined by A plus B, A minus B, B, right? So this is A1 plus B1, A1 minus B1, and then B1. Similarly, the T beta will be equal to T A2 B2, that is equal to A2 plus B2, A2 minus B2, and then B2. Let's take two elements from the field A and B. We have taken this element from the field R. And then for proving the linear transformation, T A alpha plus B beta will be equal to, it is T A, putting the value of alpha as A1 B1. So this is A1 B1 plus B A2 B2. Multiplying A inside of this bracket, A1 A B1 plus multiplying B inside, we have B A2 B B2, which can further written as T A A1 plus B A2, comma A B1 plus B B2. Now I am applying the definition of this T, this one. So first we need to sum up these two elements, then we take the difference, then comma the last one. So first element is the sum of these two, A1 plus B A2 plus A B1 plus B B2. Then is the difference of these two, A1 plus B A2 minus A B1 minus B B2. Then the last element, A B1 plus B B2. Taking A outside, we take A common from the terms. So from these two we have A1 plus B1, and now taking B common we have A2 plus B2, comma, again taking A common from this, that is A1 minus B1 plus B into A2 minus B2, comma, writing this as it is, A B1 plus B B2. Okay, let me take this bracket as this. so that there will be no confusion. And now we further write this as, we are collecting these together, a into a1 plus b1, comma a1 minus b1, comma b1, then plus b into a2 plus b2. So this is a into, this is nothing but t alpha, yes, plus b into, this is your t beta. So we have shown that t a alpha plus b beta is equal to a t alpha plus b t beta. And now we need to find the range of t. For that, if t is a transformation from v2r into v3r, to find the range we need to take one element from this. Let's say alpha vector. Then to apply t on this to get the value in this vector space. Right? Now we know that the standard basis of v2r, if I consider the standard basis of v2, that is 1 0 and 0 1, right? So these are the two vectors that belongs to v2r. Now when applying the transformation on this first vector 1 0, how t is defined? It is the sum of the two elements, comma the difference of these two, comma the last element. This is how t is given to us, right? This is how the definition of t is given to us. So that is equal to 1 1 0. So we get this vector in this v3r, right? Similarly, when applying t on 0 1, we get the sum of these two is 1, the difference of these two is -1, and the last element 1. So we are getting the another vector in this v3r space. So which means the range of t is spanned by these two vectors. So let's write this. Therefore, the range of t is the subspace of v3r spanned by the vectors, as these vectors belongs to this v3r, right? So these two vectors form a set that becomes the subspace of v3r, right? 1 1 0 and 1 -1 1. Next, now we need to find the rank of t. What is the rank of t? It is the dimension of range of t. To find the dimension of range of t, we need to get the basis for the range of t. And the number of bases denotes the dimension of Rt. That will be the rank of t, right? Now because the range of t is spanned by these two vectors, if these two vectors are linearly independent, then we say that these two vectors form the basis for Rt. So for the basis, two conditions are there. Vectors should span the range of t, and second, these vectors should be linearly independent. If these two conditions holds, then we say that these vectors forms the basis of the range of t, right? So already we have done that these vectors spans the range of t, right? Remaining to show that these vectors are linearly independent. Now V3 is a vector space over the field R. To show the vectors are linearly independent or not, let's take two elements from R, the field R. Let's say that will be x and y. And I need to show that if x into the first vector plus y into the second vector, that is the linear combination. If this linear combination is equal to 0, implies that x and y both are 0, then we say that vectors are linearly independent, right? So let's check this. This is the zero vector in V3, right? So writing this as 0, 0, 0. Okay, from here I get x plus y to be equal to 0, and then x minus y to be equal to 0, and then from the third one we get y equal to 0. So from these two I get, if I add these two, we get 2x equal to 0, implying x is 0. So y is also 0, x is also 0. So that implies that the vectors 1, 1, 0 and 1, negative 1, 1 are linearly independent. So therefore, these vectors form the basis for the range of T. So therefore, the dimension of range of T is equal to the number of vectors present in the basis. So 2 vectors are there, right? So the dimension of range of T is 2, and because the rank of T is equal to the dimension of range of T, so this is also equal to 2. So the rank of T is 2. And now for the fourth part, we need to find the nullity of T. For that, we are going to use the rank nullity theorem, that is the rank of T plus the nullity of T is equal to the dimension of U, but here U is V2R. Okay, we have just now found that rank of T is 2, and here it's the nullity of T. We need to get this. What is the dimension of V2R? We know that the standard basis for this vector space is 1, 0 and 0, 1, right? So the dimension of this is 2. So we get the nullity of T is to be equal to 0. So which implies what? It must be a 0 subspace of V2R. Yes? Otherwise, if you take an element belonging to the null space of T, suppose if I take the element from this null space of T, then we know that when applying T on this, we have to get this to be the 0 vector in V3R, right? So this implies what? What is the definition for TAB? It is A plus B, A minus B, and the last one B, that is equal to 0, 0. Okay, 0 vector. From here we get A plus B to be 0, A minus B to be 0, and B itself is 0. So that implies A is also 0, right? So therefore 0, 0, the 0 vector in V2R is the only element that belongs to V2R, which belongs to the null space of T. So therefore null space of T is 0 subspace of V2R. So here ends up the solution. Okay, thank you. Stay blessed.